Hello, this is the last part of section 9.2, and this is a little bit of applications, and this is just a very minor part. This type of course is not an application specific course. It's more of just a skill-based Calculus 3 course. However, at times we introduce some of the applications to some of the areas that we're studying here, and one of those is forces. Now, if you've taken physics, you've probably done a ton of this. If you haven't, then this might be a little bit new for you. But a force is represented by a vector because it has both the magnitude and the direction that we define vectors by. And so if we look at several forces that are acting on a particular object, the resultant force is the addition or the sum of those forces. And so we're just going to look at a couple examples here. We're not going to get too in depth. So again, if you've studied this before, this might be a little bit trivial. If you have not studied this before, you're going to be just fine. It's mostly algebra intensive. And so let me walk you through this first one. So what we have are two different forces. I'm going to go ahead and label these as force 1 and force 2. And what we're going to do is we're going to first try to represent each of the forces by a vector set of components. Okay, so if we were to take a look at, let's say, the magnitude of our first force here, we're being told that it's 20 pounds. Now we want to come up with the two components, the x and y components. Now if we look at the force itself, what we have is a hypotenuse, a length 20, that's the magnitude. We have the angle, which is 45 degrees. We have some x component and some y component. And one of our jobs here is to come up with what x is and what y is. And really, it's going to be just some simple trigonometry. So if we took, for instance, the cosine of 45 degrees, we get the adjacent, which is x, divided by the hypotenuse, which is 20. And the cosine of 45 degrees is root 2 over 2. And so algebraically, if we balance this equation, we get 20 multiplied by root 2 over 2, or in other words, we get 10 root 2. So this is actually representative of the x component of this particular force. And now what we're going to do is try to find the y component. And in a similar way, we're going to take the sine of 45 degrees, which gives us y divided by 20. So I'm just using right triangle trig here. And we solve for y, and you can, think back to all your trigonometry, which might be a little fuzzy, but it's going to be the same angle or the same value for that particular angle. And so we end up getting the same thing here, 10 root 2. And you might have thought through this a little bit and thought, wait a second, I remember in pre-calculus when you have some sort of triangle with a 45-degree angle, well, we know that opposite angle here is 45, that's a 90-degree, and all of a sudden we probably could have gotten to here using similar triangles from way back in the day, geometry, pre-calculus, that kind of thing. Anyway, now we've done it sort of the long way, and that's totally fine. Okay, let's take a look at force 2. So the magnitude of force 2 is going to be 16, which is given to us in the problem. I'm just going to draw out the triangle again. The only tricky part to this triangle is that the y component is negative because it is moving in that direction. And so when we're going to calculate the components for this particular one, we have this 30-degree angle right here. So when we take cosine of 30 degrees, and it gives us x divided by 16. Let's see, cosine of 30 is going to be root 3 over 2, and multiply that by 16, and we're going to get x equal to 8 root 3. We also have sine of 30 degrees, which is going to be y over 16, and sine of 30 is 1/2. And so what we get here for y is 8. Now, based on the context of the problem, remember when we write out our components for the force vector, or for the second force vector, we get 8 root 3 for the x component, but we get negative 8 for the y component because, again, it's it's negative on that side based on how the picture is drawn. In other words, you go down as you draw that vector. All right, so that's what we have so far to work with. We have our two different vectors now in component form. Now, our goal here is we're trying to figure out when these two vectors are working on a particular object, we want to know what is the resultant force, the magnitude of that, as well as the angle it makes with the positive axis. So our first step here is that we're going to add up these two vectors because that will be our resultant vector. And we get 10 root 2 plus 8 root 3 and 10 root 2 minus 8. So that is going to be our resultant vector. Now the magnitude of that is one of the things that we're being asked to find. And the magnitude we know is simply just the square root of the squared components. Now I think we're going to detour from doing this by hand just because it's not very necessary to practice that kind of cumbersome math at this point. Normally we would not revert to a calculator necessarily, but in this example, doing that by hand is kind of pointless. So I already typed this in. What I got is 28.664, and that is going to be the magnitude of the resultant force vector. So that's one of the things we're trying to find. Now the other thing we're trying to find is the angle that this particular resultant force vector makes with the x-axis. So to do that, let's think about it as a right triangle. Now let's actually go back up here for a moment. If we were to sort of hypothesize, where is that resultant force vector going to point? Well, this has a magnitude of 20, this has a magnitude of 16. Our angle here is actually more than our angle down here. So I'd say that we could safely say that the resultant force vector is going to be somewhere in this first quadrant versus the fourth quadrant of this plane. So because of that, I'm just going to draw a little triangle here that maybe looks like this. And what we're trying to find is the angle right here, given that our x component is 10 root 2 plus 8 root 3, and our y component is 10 root 2 minus 8. Now again, we're going back to right triangle trig. So to find this, you would take the inverse tangent. To find the angle, we would do the inverse tangent of the opposite divided by the hypotenuse. And again, you can just type this in. I already typed this in, and what I got for my angle is 12.373 degrees. So there we go. We have our magnitude of the resultant force vector as well as the angle it makes with the positive x-axis. Okay, we're going to move on to the very last page of section 9.2. Right here, we're going to tackle this problem about forces, and in this case, we have a 100-pound weight which hangs from two wires, and it's shown in this picture. And we're going to try to figure out the forces of T1 and T2, as well as the magnitudes. And so what we're going to do is we're going to start to set up in a similar way to that we did the last problem. We're going to set up our vectors as best we can in different components, and really this is different from the last problem in that we don't have the forces of T1 or T2, but we do have W, which W's vector is, so think about it this way, this force is going straight down, so there is zero movement to the left or the right. However, it's 100 pounds, which means that the J component is actually negative 100 because again it's going down and it's not going left or right. Okay, so let's start with T1. And with T1, we have this little triangle here. Let's draw it out and label it. So we have 50 degrees and Y and X. And if we're going to try to figure out the components of this, if we were to take the cosine of 50 degrees, we would get X divided by the hypotenuse of this would be the magnitude of T1. So we would divide by the magnitude of T1 here. That means that x would be the magnitude of T1 multiplied by cosine of 50. Now, when we start to set up our vector components for T1, that value is going to actually be negative because it is going to the left. So we have negative magnitude of that vector times cosine of 50 degrees. All right, now we got to do the vertical component. And so, again, I'm not going to write out the whole thing just because we had done this in the last example, and just to save a little bit of time and space. But, keep in mind we're going to take the sine of 50 degrees, which is equal to y divided by the magnitude. And so you can sort of think ahead to that. That would be the magnitude of T1 multiplied by the sine of 50 degrees. So we have the setup so far for T1. Let's do T2. And so for T2, we have the triangle with 32 degrees. And we have y, and we have x. And this is going to be the magnitude of T2. And so again, in a similar way, and in this case, I'm just going to kind of write out what it is. I'm not going to do all of the algebra attached. But what we'll find with the first component is that it's going to be the cosine of 32, which is going to be x divided by the magnitude of T2. And if we were to solve for that x component, we would get the magnitude of T2 times the cosine of 32 degrees. And vertically, we would get the magnitude of T2 multiplied by sine of 32 degrees. Okay, so this gives us the components of each of these vectors. So those are going to obviously both be very important. Okay, let's think about the relationship then between these vectors. So we have a 100-pound weight that hangs from these two wires. It doesn't break the wires, which means that the vector T1 added to the vector of T2 must equal vector W. The components have to equal each other. So in other words, if we were to take the first component of T1, which is negative magnitude of T1 times cosine of 50 degrees, plus the first component of T2, which is the magnitude of T2 times cosine of 32 degrees, that must equal 0 because 0, back up here, 0 is the first component of W. So the first component of T1 plus the first component of T2 must equal the first component of W. So this is an equation, a true statement, and yet there are still two unknowns, which means we can't quite solve it yet. However, we can do the same thing with the second component. So the second component of T1 plus the second component of T2 must equal 100. Now the reason that this must equal 100 is because when we were to add these up, we would need to make sure that we get 0 when we look at these two vectors in conjunction with the weight, because again they're holding the weight, so that means that they must take that weight and support it. And so these two vectors here that we have must have a pull upwards of at least 100 in order to balance the weight which is pulling down at 100. So what we have here is a system of equations that we need to solve. We need to figure out what these magnitudes are. And we can do that a variety of ways. I think what I'll do here is I'll take the very first one and I'll just set these equal. And maybe let's just solve for the magnitude of T1, because we need to solve for one of them. So that's going to give us the magnitude of T2 times cosine of 32 degrees divided by cosine of 50 degrees. And then we use substitution here. We're going to take that and substitute that in to our second equation in order to solve for one of our magnitudes, and then we'll be able to kind of go backwards and solve for the rest. So what I'm going to do is I'm going to pause this and write out this phrase, and then I'll come back in a second. Okay, so I just kind of went through and wrote out the algebra here. It's kind of an intense algebra problem. So I did the substitution for T1. That gives us this equation here, which has just one variable now, which is just the magnitude of T2. So then if you factor out the T2, the magnitude of T2, and move everything over, you get this large equation, and if you use your calculator, you'll get the magnitude of T2, which is 64.910. And again, that's kind of intense there, which is you're going to find is pretty common in our course to have some relatively ugly algebra problems. But then what we're going to do is we're going to go back to what we had up here for magnitude of T1, and we'll just take this 64.910 and plug that in, substitute that in for the magnitude of T2 in that equation. And if we do that, what we get for the magnitude of T1 is 85.638. So there we go. We have our two magnitudes. We're almost done with the problem. We just have to figure out what our vectors are, what our actual forces are. So now that we know what the magnitudes are, we can go back up to our equations here for the forces. So we have our T1. Now we can plug in the magnitude of T1, and then we have T2, and we can plug in the magnitude of T2, and we should be finally done. So if you use a calculator to do so, you will get negative 55.047 and 65.603 for T1. So there are the components for that particular vector. And then for T2, we have 55.047. Remember, that's important because these two components need to equal 0 when you add them up, because this weight didn't move left or right. So that's a good thing that we have that decimal match up. And then we have 34.397 for the second component. All right, we have finished section 9.2. Excellent job. And we will move on to 9.3 during our next class. Thank you.